Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemistry, the only podcast that combines geochemistry and the tea. And no, we're not talking about the tea that you drink, but good old-fashioned industry gossip. Each podcast will feature one of our own, from the famous to infamous to obscure. There are so many questions and topics that geochemists need to air, and here at Geochemistry, we're providing the platform. Our structure is simple. We'll introduce our guest, and they'll explain how they made it through the red tape to break into geochemistry, and if they can do it, you can too. We'll then move on to tea time, followed by a review of a geochemistry paper and a larger discussion around that topic. We hope to inspire and to help. And now, without further ado, I'm your host, Sam Scher, and this week we'll be talking with Simon Griffiths about the oil-bearing Carlin-Type gold deposits of Yankee Basin, Alligator Ridge District, Nevada. Simon Griffiths is a consulting economic geologist and the director of Third Planet Exploration Services. Simon, welcome to Geochemistry.
Hi, Sam. Thanks for inviting me on.
Simon, from my recollection, you grew up in Wales and now you're back again?
That's right, Sam.
A bit of an unusual spot for a geochemist, but it says a geochemist living in Washington, D.C. So I guess what everybody just wants to know, what's your journey been and any red tape in getting into the field?
Yeah, well, it has been a long journey. Really, my master's dissertation, probably not many people know this, but it was on a structural geology focus. So my first job in Mexico really was probably because I had a lot of experience or at least some knowledge with how the various mineralizing systems work from a structural perspective. So how did that jump to geochem? Well, this was back in the early 90s, and what became popular were interpreting those thematic map Landsat images, the new satellites from back then. So I ended up doing all these lineament and structural interpretations on the satellite maps, but I also then realized that, it's multi or hyperspectral data, and there was an awful lot more than just landforms and lineaments. So to cut a long story, hopefully a little bit shorter, I ended up messing around with the spectral side of things and generating these anomalies that I thought were relating to alteration in the field. So I went out as a field geologist and did some ground truthing with my PIMA spectrometer. And that got me into mineralogy and chemistry and mineral chemistry. And a few years later, someone came through from Rio Tinto on a review and said, hey, we need a geochemist for North America. And I recommend Simon is the geochemist for North America because he's got this interest in the minerals and the chemistry and the alteration. So anyway, they picked me out of there and sent me to Australia for a couple of months where I got trained up on all the Rio Tinto CRA way of doing things and approach to exploration geochemistry.
That's really interesting. Definitely different than my journey, but this is about you. So I guess following that, do you have any tips or advice to give our listeners that want to break into the field of exploration geochem?
Well, I think, it's one of those sort of adages in the industry that, everyone's a geochemist, but no one's really a geochemist. So, we're all geochemists as exploration geologists because we're all out there actually acquiring geochem data in the form of every time we walk up to an outcrop, we take a sample as well as taking a structural reading and writing down what we see on the outcrop. A lot of us are collecting soil and stream sediment samples as well. So of course, then all those samples go to the labs, and rather than treating the lab as a black box, I just encourage everyone to try and understand a little bit or just get a working knowledge to begin with of what's going on in the lab with the samples in terms of the sample preparation, but also the analytical techniques and the various different options you've got for dealing with various different types of material that you send into the lab.
So this sounds like a whole different podcast episode that I guess we'll circle back on.
Please don't say circle back.
You're welcome.
God. Let's pivot the conversation.
All right, so we're going to pivot now to talking a little bit about some tea. I have the unfortunate advantage here that I could dish some tea on you. So definitely tread carefully on what you're about to say. I figured I would include this section both because I love the phrase the T, but also I think it's really important because I think us as geochemists, we just seem so unobtainable to the common geologist. So I figured let's just bring ourselves back down a little bit, humble ourselves, and just, give a little bit of tea. So what's some good tea that you have?
Yeah, well, Sam, bearing in mind that you've got some tea on me, I might as well be proactive here and just go after myself. um, I don't know, there's probably plenty of tea out there about me, but since we're going to be talking about Carlin deposits, then it brings to mind a few experiences in Elko and in that sort of neck of the woods in northeast Nevada. I don't know. When I was living in Australia and I was the Barrick chief geochemist, we didn't have a geochemist in North America at the time in Barrick, so I ended up traveling over about 3 or 4 times a year. And in fact, obviously the people in Barrick knew that I was over from Australia, but we used to spend quite a bit of time in the Stray Dog in the bar there in Elko. And of course, if you're a geologist and you don't work for Barrick and you live in Elko, you probably work for Newmont. Well, certainly you did about 10 or 15 years ago. So the people we would hang out with at the bar, the Newmont guys, they got to know them quite well and actually, kind of friends with them and stuff. And anyway, after a year or two, one evening, I just mentioned that I was going back to Perth the next day. And they kind of looked at me and they said, well, what are you going to Perth for? I said, well, I live there. And they said, no, you live in Elko. I was like, no, I live in Perth. I got a family and everything. And they're like, no way. Every time they said to me, every time that they were in the Stray Dog, I was there. So I must be from Elko. So there you go. I was a bit of a regular there for a few years.
I mean, I guess that sounds pretty interesting considering that you were in and out, but you were there enough that they thought you were local. So
yeah, and I was there just as much as the guys who were based there because, of course, then they were traveling elsewhere to their field projects. And I guess when they were back home, it wasn't all that often. So
I guess the takeaway then is that geochemists are just like geologists, and you can find us at the bar.
Yeah, exactly. I think the one thing most geologists can agree on, we can't agree on what the rock type is, but we can usually agree on which pub's going to be the geopub in any given city, right?
That is true. And even rename them to be the geopub.
Yeah, just keep saying it.
Yeah. Great. Okay, so I guess we'll just move on now and we'll talk a bit about the paper that we'd selected. The idea here is that, we have the paper as something to reference to, but at the same time, I don't know how many people know the infamous Simon Griffiths, but he's, as we just heard from all the discussion of Elko, he's probably one of the exploration geochemists that knows the most about the Carlin deposit. So this should be a really interesting discussion for me anyway. I remember distinctly first meeting you, though, and it was back at the Association of Applied Geochemists conference in Tucson. We were both in the short course, and the topic of gold in the Carlin came up, and I asked a question about oil as a complexing agent in the Carlin. I don't remember receiving a hugely satisfying answer, but afterwards, you and Jeremy Vaughn, who's another geochemist, came up to me and were like, tell me everything you know. And I was like, I know nothing. So then here I suggested that we read the oil-bearing Carlin-Type gold deposits of Yankee Basin, Alligator Ridge District, Nevada, to dive into this topic. And I'm really thrilled that you agreed to this. So geochemists, you're in for a treat because Simon is arguably the reigning exploration geochemistry expert in Carlin. And I guess, would you like to start by giving a broad overview of what makes Carlin deposits geochemically interesting and different? And then move into your top highlight from the paper to get this discussion really rolling.
Yeah, well, thanks, Sam. I mean, that's a very flattering intro, another intro. Look, there's definitely other geochemists working on the Carlin deposits, and we've done a lot of research, and I think maybe we might touch on this a little bit later on. But there are the guys, John Muntean and his group in the UNR, and then, of course, Sean Barker and Ken Hickey and the guys up at UBC who've been leading a lot of the sort of more, I say academic, but also there's a big practical side to the research they're doing. And then I think probably, you've got the in-house geochemists as well. So, but for the big companies, so, you don't often hear about really what they're doing. They don't really necessarily talk much about what they're doing or publish things. So, and as you mentioned, I was part of that. So, keeping information in-house and keeping sort of your competitive advantage becomes a little bit more important than standing up and really telling everyone what you're doing. But in terms of broad overview of kaolin deposits from sort of geochemical perspective and what make them different, I think really for me, and you hear this all around town in Elko and in all of the sites you go to, is the favorable host rock. So, of course, you also hear things about structural intercepts and structural settings and trapped site scenarios and things like this, but really you hear often, more often than not, about the so-called favorable lithology. But the thing is, if you go to a district, a big district like Cortez or Goldstrike district, for example, that had multiple deposits throughout the district or throughout the camp, and if you go and ask, if you get a strat column and you go around the various geologists' office and you give each one a pencil and you say, mark the favorable host rock in this district on this strat column, and they'll mark it against their favorite one, the one that probably is the host rock at their particular deposit or they're working on. By lunchtime, if you've got yourself around to all the geologist's office, you're going to sit down and look at your strat column, and it's going to have a big red line all the way up the strat column, in the lower plate, the Paleozoic rocks at least. And that's because all of the formations can be favorable host rocks at any given time in any given scenario. And I think, from my perspective, what makes them different is that, or makes them favorable in any particular place, is these facies changes within the formations. And because of all of these formations are these marine sediments that have accumulated over millions of years, of course, these types of environments are sort of famous for their facies changes within them. So a particular favorable or reactive host can occur in a particular facies, and that particular facies can occur in any of the formations that you get anywhere in the eastern sequence. But also, I've seen them because now I've been working in the Walker Lane, and I've been working in the western sequence as well in Nevada, and we have very similar scenarios there. The packages or the formations in that part of the world can also throw up or present these favorable facies. And then it's not restricted to Paleozoic either, because further north, like in southern Idaho and northern Nevada, you've got Mississippian and Perm age marine sediments, and then the same actually in Yukon and northern BC. So actually it becomes more of a generic process-driven sort of thought process, rather than just having a favorite name. Or, I like the Wenban Formation, or I like the Horse Canyon Formation.
I guess then, kind of going back to the geochemistry of this, and now that we're talking about how all these deposits, they all have different host lithologies that are all similar to some degree. Is there anything that you've seen in the geochemistry that you can separate them out as to be distinct, and maybe that you could say that potentially this one would host something that has a larger deposit because it has something more geochemically distinct?
Yeah, that's a really good question, Sam. And the thing is, that's a question that has been posed in different types of systems as well. So obviously people working in high sulfidation epithermal systems and porphyry systems, they want to know what are the fertility indicators, and then what are the giant sort of indicators. So is this a fertile district where I might find an interesting ore deposit? And then secondly, is this going to be a big deposit, or is it going to be a small or sort of average sized deposit? And those are very pertinent questions in the Carlin as well, Carlin-Type deposits as well. And What I've noticed since I've been working with Barrick is that there are some conditions that are permissive to gigantic Carlin-type deposits. That was when I was with Barrick, and there's only quite a specific range of conditions in the marine sediment column that will host a gigantic deposit. But since working for Barrick and working on other projects and smaller deposits, I've realized that there are far more circumstances or conditions that are permissive to hosting a 1, 2, 3 million ounce deposit. So it kind of opens up for me anyway, in my mind anyway, a lot more search space in the marine sediment sort of column, because you don't have to have the very specific sort of redox conditions necessarily for a giant. There are other conditions, a broader range of conditions that will permit the accumulation of smaller gold deposits that also move the needle for a junior company.
And so you mentioned redox, which is, I love talking about redox. So we're talking marine sediments, perhaps a bit reducing. Is it a very small range, or is it a larger range that we're looking at here?
Well, I would say it's a fairly large range, but that's obviously a very subjective kind of statement, right? So there's quite a lot of literature in the hydrocarbons field where their main concern in terms of favorable host rock is what's the favorable reservoir rock. So what kind of sediment would be do you want to look for that would be in a trap site that might host an oil deposit or accumulation of oil or gas? And so they use these redox sensitive trace elements. Some geochemists or exploration geochemists in hard rock refer to those, or might know those, as organometallic sweet. But it's basically the same thing. So I've been using the term redox sensitive trace elements because you can play around with those and make an acronym that's ROSTE, ROSTEs. So I've been trying to sort of coin this roasty phrase for a bit, but the point being is that you've got elements such as uranium and moly, or chromium, vanadium, a few of these types of elements, and really they can exist in the water column in quite a few different valencies. So in fact, you can even have molybdenum 4, valency 4, uranium 4, and chromium 4 and 1 and 2. So really the valencies that these elements exist as in the water column are reflecting the reduction oxidation conditions of the water column itself. Now, when these when the sedimentation is going on, depending on the depth of the water, that's what kind of relates to the redox conditions of the water column. Then these elements will deposit or absorb into the sediment at the bottom of the ocean in different valencies, and so they will, in some cases, they will be a sort of more taken up or absorbed by the sort of sulfidic nature or organic material at the bottom of the ocean. So and then to different degrees. So what happens is that over time, and then when you're looking at these rocks later on, when they're all now marine sedimentary rocks, you can look at things like enrichment factors of these elements as compared to things like Clark values, and you can say, well, look, here's a package or a sediment or a unit or a facies that's more enriched in chromium or moly or something like that, with respect to the other facies around them. And you can also play games with things like phosphorus, because the sediments that we're talking about from the Cambrian and Ordovician onwards, there were lots of, and of course an increasing amount of marine life. So when the marine life is swimming around near the surface, but in deep water, then of course these little critters die, their skeletons fall to the bottom, and you start to get an accumulation of phosphorus. And then the phosphorus will accumulate in different parts of the basin, and depending on the amount of life that's in the water column as well, and the redox conditions at the bottom of the ocean. These redox conditions can also change in the same place over time, because the basin might be somewhat constricted, it might be completely open to the wide ocean, or it might be, completely cut off for a while. And there are lots of modern day analogies to those sorts of basins. So anyway, this is what basically causes one of the causes for the differences in these host rocks.
That was really interesting, Simon. A bit of a diversion, but things that I had never thought of, working so long in magmatic hydrothermal systems and not really focusing on so much of the marine sedimentary environment. That said, I guess one of the things that I found interesting, and I think that you did too, was one of your top highlights from the paper, which had to do with temperature. So is there things that you can expand upon about that?
Yes, that's a really good point. One of the big things I think in this paper, even though it's an older paper, talks about how the Yankee system, based on the paleo temperatures from taken from what could not have been surpassed in terms of paleo temperatures in the hydrothermal system, because the hydrocarbons have not matured. So they're talking about a maximum temperature of 145 centigrade, which is a lot lower than the sort of generally held, even today, I think, generally held view that the Carlin systems would have had to have formed a little bit hotter than that. I think still there's probably a lot of people thinking that sort of 200 to 250 C might be sort of the temperature formation of the gold deposits, and of course that's a lot higher than 145. So that really is interesting, and I mean, it's also interesting that this paper is from, sort of 1999, and that little tidbit's been sitting there all this time, and maybe not fully followed up on.
Yeah, it is interesting too, because the paper is in the SEG, so it is interesting that it doesn't seem to have been followed up on in your estimation anyway. Another thing that I found that was interesting, so we talked quite a bit about the geologic setting at this point, but there's a reference in the paper that igneous intrusions occur near to or within many Carlin-type deposits. And I'm just, from a person coming from a situation of not knowing, what is your take on whether the mineralization is a distal magmatic hydrothermal process, or that the gold-pluton connection is maybe just coincidental?
Yeah, I think, well, again, not before I sort of answer that, there's definitely still two camps, okay, where there's a group of people who very adamantly believe that the deposits are very closely related to the so-called magmatic sweep in Nevada that sort of swept on if you imagine a northwest-southeast sort of line sweeping across from Elko all the way down to sort of the Bullfrog district, from about starting to probably the low 40 million years old, 40s, something like that, to almost sort of 10, 12 million years ago. So there are papers on that, Gene Klein and John Montine, for example. There's some classic papers talking about that. But then, of course, you've got the other school of thought or field or camp that, talk about it being just not really related to that, and to be more of a basinal type scenario. So, do you have a series of sediments that are already sort of primed in terms of having enough diagenetic pyrite and other sort of ingredients, so that they're just primed and waiting for some ore fluids to come through? Because of course, with the ore fluids being of the similar age as that magmatic sweep, at least in northeast Nevada, the 38 to 42 sort of million years old. Excuse me. So anyway, what do I think? Well, I wouldn't put the intrusive or a spatially a temporarily related intrusive as necessarily being a must-have. Either because in some deposits you don't see them, either because we just haven't found them yet, or because they're not there at all. So I mean, I wouldn't necessarily use that as a huge indicator.
Okay. Switching gears here, I found the alteration and mineralization section of the paper unfortunately broad. Can you offer any other insights into the alteration and mineralization of the Carlin?
Yeah, sure. I mean, just for the listeners out there who might not be all that familiar, I mean, generally speaking, with the Carlin systems, there's an initial fluid flow, which essentially it comes through these marine carbonates, and there's the term decalcification is out there. So really what the fluids are doing, they're acidic enough to leach out some of the carbonate material, the calcium carbonate material, and leave a certain amount of porosity or an enhanced porosity through the rock mass. And as I said before, with certain units or certain facies within the formations would be more conducive in any case and more reactive to this fluid flow. Once you have the first pulse of fluids coming doing the so-called decalcification, the mineralizing fluids come through, and they generate silica. So then you have a silicification, which is not as broad as the normally not as broad a halo as the decalcification, but is broader than the deposition or precipitation of gold and some of its pathfinders. So from an alteration perspective, in terms of fluid flow, you'll see a larger halo of decalcification, and then a smaller sort of alteration zone of silicification, and then within it you'll start to see zoning of the pathfinder elements for gold. And when you get pretty close in, especially to the structures or to any faults that were active in and around the alteration system, the mineralization system, you'll start to see illites, for example, maybe some ammonium illites and things like this. So you'll see more smectites on the outside and then illites, close in as well. So there's a fairly well documented alteration sort of pattern around these systems.
That's really interesting. I guess talking about ammoniated illites, did you guys really only notice those from using, say, the Pima and then moving into the Terra spec, or is there another way that you guys were identifying them?
No, for sure. I mean, that's really the only way you can do it, right? I mean, you use the hyperspect. Well, not the only way you can do it. You can get XRD and stuff, but the portable or the semi-portable sort of multispectral units, that's what we were using in Barrick, and we had someone working on that full time. In fact, probably a couple of people working on that on and off, and some of the papers out there came from those people's work. So the thing is, if you use that in conjunction with the geochemistry, so for example, if you have a sampling program and you're collecting, let's say, four acid or multi-acid data for your trace elements, you're doing gold fire assay, and then you're also doing the spectral work. So you're looking at your sort of illites, let's say, and sericite composition and crystallinities. When you merge all of that data together and you start looking at the spatial patterns, you can really start sort of honing in on where basically the hot acidic fluids were moving. And then all you got to do is follow the fluids to a trap site or a favorable horizon, and then you'll find where it's precipitated, where the fluids have precipitated the particular minerals. Now, you could argue that once you get to a structural trap site that's where the hot acidic fluids have been pooling or potentially precipitating, and you see trace elements and pathfinder elements such as arsenic, antimony, and thallium, but no gold, you might say, well, I had the wrong fluid in the right place. or you might go somewhere else and you say, well, I've got the right fluid, but in the wrong place because I've only got traces of gold along this structure and there was no trap site or no sort of chemical or physical structural trap site. So, it's just a way of maybe thinking about the mineral system as a whole and not just chasing small ore bodies, because don't forget, these are high-grade deposits. So you can fit a lot of ounces of gold in a very small space if you've got 10 to 15 gram per ton material. And so it's pretty hard to find the small, a 1 to 2 million ounce deposit because they're so small at that grade. But if you think about a mineral system that you're chasing, once you're in one and you can recognize one, then you need to navigate around. And that's using, obviously, the structural geology, but we're talking about geochemistry here and alteration. So using these tools that we have readily available to us, we can use the mineral chemistry, use the geochemistry, and follow the pathfinders and hopefully find where the gold's being precipitated.
Those are really interesting points, and I'm glad that we spoke so at length. I didn't think that we'd get so far, but one of the other things I wanted to talk about in the paper was just, I was really looking forward to the author's hypothesis on how the gold was moving and precipitated in Alligator Ridge. But unfortunately, despite the title, it was outside the scope of the paper. So I did some additional digging, and I didn't realize that in '99, when the paper was accepted, that there was not really a good way to analyze the fluid inclusions for hydrocarbons, which could have been a really interesting part of their story. This paper, however, it did have a large section on fluid inclusion work. And I was just wondering, for working for so many large companies, how did you see the application of works like this?
Yeah, that's a good question, Sam, because then you get to the point as well, what is sort of academic research and what is application of new tools to reduce your exploration search space and all of those sorts of things that you're trying to do to save money and get to the discovery sooner. In terms of fluid inclusions themselves, to be honest, certainly over the time that I was working in the larger companies, up until a few years ago, we didn't really use a lot of fluid inclusion work, to be fair. What we did do, though, is we did, a lot of the mineral chemistry work, which then became part of the regular toolbox. But also, we did quite a bit and sort of helped or co-sponsored some of the research that they were doing at UBC, for example, around isotopes and stable isotopes. So I was just talking about decalcification being sort of one of the broadest, sort of spatially broadest zones of alteration. But actually, if you look at some of the literature coming out of UBC from, like, again, 5, 6, 7 years ago, you can see that if you look at oxygen and carbon isotopes, for example, they have a much wider footprint. So there's a large oxygen isotope depletion zone that goes way beyond the extent of the decalcification. So again, if you're looking for a mineral system or a great big sort of freeway where fluids have been flowing, at least there's been some heat, hot fluids anyway coming through, then that might be a more far-field approach.
So then, I guess, talking like this, do you see more applications to use some of these more academic type things in larger companies? It just maybe has to be a little bit demystified better. And what's your thoughts?
Yeah, no, I think there needs to be, and it's really valuable to have this sort of pipeline of research that's going on that is then applied to the practical scenarios. So, that pipeline is established, like I said, with groups such as the Craig, in the UNR and the MDRU in the UBC. That's lots of acronyms, I know, but basically Reno and Vancouver. And companies, co-sponsoring and sponsoring people doing their masters, dissertations and theses, for example, and PhDs. Obviously, there are some smaller companies that also participate, but sometimes the price tag is just a little bit out there in terms of trying to convince shareholders that this is not just philanthropy. But what happens is that, what this does is it generates these new tools. Obviously, not everything is going to work, and not everything's going to be practical, or not everything can be sort of commercialized in terms of a service that then we can all use. But I think it's a really important pipeline. I think some of the tools that we're using now in mineral chemistry, for example, and even some of the analytical techniques maybe that have been finessed with the labs, those are things that are making our path to discovery a lot shorter. The other thing that I think is underused is things like just very simple stuff that reflects sort of zoning and things like this. For example, looking at the UV response or the CL, catholuminescence response to things like the calcite veining, and how the calcite veins sort of change, or they're manifested in different ways through the deposit. It's something that people have been talking about and using in porphyry systems, for example, probably for a long time. But these are things that some people are also using in Carlin, and it can be a very simple tool that can be applied and be very useful. You can take your UV light, and you can have, as we already collect, pretty much everybody is collecting photographs of the core all the way down the drill hole. Well, you can have a quote-unquote normal photograph next to a UV photograph of the core, and create that as another record of what you've drilled, and then use that to come back and compare with the chemistry. So if you see, for example, changes in the UV response from calcite that reflect differences in the vein chemistry or the calcite vein chemistry, you can maybe then map your way around the system as well.
So what kind of colors are we talking about? You say UV and I'm thinking purple. Are there different shades of purple that we're looking for? Or did it light up orange?
No, with the calcite, I guess one of the sort of the terms people use is fire engine red.
Oh, wow.
So, yeah, when you see the calcite really fluorescing bright red color, there's going to be some inclusions or impurities in there. It could be reflecting. There's various different types of impurities, if you like, that could be in there. But and again, MDIU, they've done quite a lot of. There's a few things put out by them in short courses and things, but any tool like that that's just simple to use and has a real sort of foundation in, you can relate it back to the rocks. Okay, so it's not just, I got these pretty red colors and I like those, so that's where I go exploring. It's like, well, no, that you can tie that back to something that's going on, a process that's happening in the rocks that is reflecting, again, the mineral system or the mineralization or the alteration that's happening. Like I said earlier, you've got the decalcification. All of that calcium carbonate's got to go somewhere. And so you end up, somewhere in the system, you're going to have a massive amount of calcite veining.
It's a really interesting point. And I guess, thinking about it maybe a bit too practically, you have a geologist log, or they logging then that, from here to here, they had fire engine red calcite veins. And then from here to here, they had, a different color vein. And then that's how it's being, driven into their model so that, you have that whole mineral system.
Yeah, well, it depends on how you're using your geological and geochemical data and how you're modeling that up. And, again, that's yet another
I know.
podcast.
I had to do it, though.
I'm going to try and sort of hold myself back a little bit on this. But for me, and, I am a geologist, so I'm just qualifying that, nowadays, the sorts of really good quality analytical instrumentation we have available to us at the labs, and the labs are all, the labs we're using are ISO accredited, and the methods are published and validated and calibrated and everything. So what the geochemistry brings to the table, apart from everything else we've been discussing today, is a systematic and quantified and quantitative set of data that can obviously be modeled because it's just numbers. So if you can relate whatever you see in, say, a UV response or in any other thing that you've seen, maybe it's a visual thing that the geologists are logging, if you can relate that back to a number or a ratio that's in, let's say, the geochemistry, then that's far more you can model that far more systematically in your 3D or in your sections or your level plans, then you maybe would be able to just an observation, or so someone says, well, this is redder than that, or this for me is red, and for somebody else it's orange or something, right? So,
Yeah.
but if you've got something numeric in there to model, then it makes it a lot more repeatable and robust.
Another thing missing from this paper was discussion on rock composition. In your time working the Carlin, what type of geochemical analysis did you employ?
Yeah, thanks, Sam. The analysis that we employed were basically, I mentioned it before, but 4-acid digest, basically trying to get as much, as a total digest as possible, and then as getting as large an element suite as possible. So, and I say as possible, there's obviously time and cost constraints. So you say, well, okay, then why didn't you do, lithium borate fusion whole rock for everything? Well, it's cost prohibitive to do that on 40 or 50,000 samples when you're drilling out a deposit. So, the 4-acid is I like it because it's a nice sort of compromise in terms of cost, but at the same time, you're getting a lot of really good data, and you're getting quantitative data for most of the elements in the suite. And of course, the analytical finish can either be on the ICP or on the mass spectrometer, depending, which element, if you want to, if you're interested in some of the sort of lanthanides and things, then you need the mass spectrometer pretty much. But otherwise, the ICP finish is normally good enough. You do, though, need to be consistent and systematic about the way you're doing it. If you're going to apply that as a method, then you really must, continue to, run with it, sort of thing, right? So some people will say, well, hang on, why don't we, that's expensive. I'd rather just do gold assays, which is, expensive enough as it is, and maybe I can just do a few pathfinders. Well, or then if you, come in and you recommend a larger suite that's a bit more expensive, then people will say, well, why don't I just do that every 50th sample or something like this? Well, okay, in my opinion and my experience, I kind of don't like where you have just a sample every 50th, or one sample every 50 feet or something that has the multi-element, and then you've got all these samples in between that have gold assays every 5 feet or something. So what I like to recommend to people is that they composite the samples. So you might have 5-foot intervals, for example, for gold fire assays, but then you could composite 3 or 4 or 5 of these samples together. So you have the multi-element is on a 20-foot composite or a 25-foot composite or something. So you have got continual geochemistry down the hole. It's not spotty, every nth sample, but it's composite. Now, I think that the sorts of variations of sort of chemostratigraphy and the sort of variations in alteration and pathfinder mineralization that we've been talking about, you can see those on that scale. So we don't necessarily need the spatial resolution of 5 foot to be able to map out and model these systems. We can step back and do a 20-foot composite, and we can still see where the fluid pathways were and where the favorable host rocks are, and plug that into our follow-up exploration.
And one thing also that happens in drill programs, I think a bit too much, but I'd still like to have the conversation, is I think there's also just a bit of confusion of, do I get an aqua regia or do I get a 4-acid? And so you can see that there is some difference in them, but I think that perhaps that the labs don't do a good enough job of educating people of what exactly the difference is between the two digests. So could you just give us a bit more of an understanding about what differentiates the two, and why you, as the chief geochemist of Barrick, or now as a consulting geochemist, would recommend getting a 4-acid versus an aqua regia?
Yeah, so the way I like to think of this is, again, I hate to sort of keep going on about the structural geology analogies, but I think we could all probably remember from school how structural geology is fractal. So you can look at a fold or fracture or foliation in in a thin section, and then you can look at the same pattern in the hand specimen, and you can go to the outcrop and see the same pattern there. And then you can get in the plane and you can look at the whole mountain range, and it's repeated on all these different scales. So that's what we mean about structural geology being fractal. So it's not a direct analogy, but I kind of like to think of geochemistry in a similar way in terms of what's going on and what these various acids and fluids have been doing. So if you think of something like metamorphism, which is isochemical. So you have metamorphism comes in and it really doesn't change the composition at, let's say, at the scales that we were talking about in the last question. It doesn't really change the chemical composition of the rock mass. When you have metasomatism, which is another word for hydrothermal alteration, it is not isochemical. What we've been talking about today, removing calcium, adding silica, adding thallium and gold and arsenic and all these other things. So that is not isochemical. So, but what is moving these fluids? What is moving these elements around? Well, these are fairly hot. Even given this paper, we're still, let's say, 150 odd, or maybe if you talk to other people, up to 250 degrees centigrade fluids that are very low, pretty low pH. So you've got pretty hot and pretty acidic fluids. Okay, so then the rocks are there, and the mineral deposits formed and everything. We come along and take a sample. We send it to the lab. It gets crushed. It gets pulverized, and we put it in a test tube. So if I put in the test tube with that sample, if I put aqua regia, so that's just two acids. It's hydrochloric acid and nitric acid. What I'm being able to mobilize in that test tube is whatever was mobile in a weak acidic, basically an aqua regia type fluid in the ore system. Everything that was not mobile is now not mobile in my test tube either, in the weak acid. But what I want to do is I want to put in another couple of acids in there, the hydrofluoric and the the sulfuric. So I've got my four acids, and now you've got a really potent low pH. And the other thing about adding more acids, they don't just throw all these acids in at once and just put it in the microwave. These digests go through various cycles of heating and cooling and going to dryness or incipient dryness and powdery, and then being redissolved again, if you like, or redigested with the next acid, and then it goes up to temperature again. So this is like pulses of different acids coming through in your hydrothermal system. So the same elements that were mobile during the hydrothermal system are now mobilized and dissolved in your test tube in your lab. And then you aspirate them into your analytical instrument, and then they're all mobile and they're all available to be analyzed. So that's kind of a long-winded approach, and that's the way I think of it in terms of how do we replicate what was going on in the mineralizing system, in the hydrothermal system, at the lab, so I can actually see what was going on back then. And if I only use something like aqua regia or a weaker acid, okay, I'm not getting the full picture. So there is a difference in price, and obviously I'm not going to quote prices because it's different from different labs, but the variation, is definitely there. The thing is with the variation in price, it's there for everyone to see. All you have to do is go onto any lab's website, and you can see aqua regia is X dollars and the 4-acid is Y dollars, and there's a difference. So when you're doing your budgeting or you're talking to your manager, you say, well, why do you want to spend an extra X $1,000 on analytical geochem or at the lab, when we could be doing another drill hole or building another road or doing something else? And so the thing is you're just looking at the cost. The difference in the value that you get from only looking at, let's say, the aqua regia digestible side of things, or looking at the full picture, the 4-acid sort of scenario, is that with the aqua regia, you're going to be able to look at things like your pathfinder elements. You're going to be able to map, the anomalism in your arsenic, in your antimony. You're going to be able to look at decalcification, maybe, if you look at your calcium numbers. But you're not going to be able to really do much else. If you have your 4-acid where you've digested, the grand proportion of the rock, so a much higher degree of the rock, now you're going to be able to do things like the chemostratigraphy we were talking about earlier, defining the various facies, where the favorable lithologies are, where the near misses are, because if you drill through a favorable lithology that's had fluid flow, it's either an exhaust or it's a trap site that's, had the wrong fluid, that has not been all gold bearing, and things like that. So you can really put together the geochemical sort of framework that we've been talking about today when you've got a much better digestion. The other thing about having more detail on the in terms of being able to do the chemostratigraphy is that then it gives you a lot more optics on the juxtaposition of different lithologies or formations together. So you might have similar formations, different facies or different units, and then you start to see structural breaks and things like that you wouldn't necessarily have seen just by looking at just the pathfinders with the aqua regia. So I'm a big fan of 4-acid. It's what we were doing back in Kennecott, Rio Tinto days in the late 90s, pretty much as soon as it came out, and the early noughties. And then when I started working with Barrick, it was just a case of, right, let's just make sure everyone's doing the 4-acid. And, sometimes I did have some discussions with the managers, and they're like, why would we increase our cost? We're sending a lot of samples to the lab. This is a big cost increase. What's it going to show? Do a cost-benefit analysis for us. So, well, until I have the data, I can't really show you the value. So I can't really do a proper cost-benefit analysis, but, trust me. So eventually, all you need is one site or, one group to start doing it, and then you can show the value you get from there. And when other people see that from other sites, well, why haven't you done that at my project? Well, because you're still doing aqua regia, that's why. So, once people start seeing the real value from these analyses, then the cost kind of justifies itself.
Yeah, I think that's often a problem that we see, not just as geochemists, but anybody trying to bring in, even if it's an old new tech, trying to bring that in is always it's very hard to get initially. But then once you get it across the line, then everybody starts to really fall on the train, because then they could really just see, what the power is of using these new technologies. Yeah. Thanks for sharing all that. It may have been a little bit long-winded, but I don't think it is really to people that are listening, because these are things that where is that written anywhere, right? So I think having your experience and sharing with that, I think that is pretty meaningful to listeners. And listeners, feel free to send us a little note about that, some feedback. I think we've really touched on a lot of the different points of this paper that I really wanted to get out, from different things from the Carlin, different things about some of the hydrocarbon situations. Also talking about, which was unexpected, but ending up talking about some of the research and industry and how that plays together. I think that those are all really important things. And geochemistry, like other parts of geoscience, is always evolving. So I'm definitely in agreement with you with some of these projects that have been going on. I think maybe just to open up one last crack, one last big bag of worms or whatever the phrase is at this point. I think I would just like to end off by just asking you, and maybe could you answer it in 5 sentences or less as a challenge, but any thoughts about models generated over the years about Carlin formation and deposit style?
Yeah, I think generally speaking, I'm not a massive fan of model, and certainly not model-driven exploration, because I think there are all of these so-called beasts out there that we just haven't found yet and we know nothing about, and they will be off the chart, or they'll plot outside the diagram, or outside the template. But having said that, there has been a lot of work done, and the models around the Carlin systems that we see published in the last few years are really useful. So things like I've tried to mention today in terms of how do you navigate around a mineral system? that might be hosting a Carlin-Type deposit. How do you use chemistry and structure and lithology to get to where you need to be and get to the point that you need to test? I mean, we know that there are certainly certain scenarios that are permissive to the deposition of a Carlin-Type deposit. So, we can read up on those and we can go and explore for those. As people do more and more exploration, then we'll come across other examples and other scenarios that are sort of outside of the template, and we'll just add to it. But the way of doing that is once we do make our discoveries, that we involve the researchers and that we partner up with these guys, and that they can come in and they can do their fluid inclusions or their stable isotopes or their fission track appetite analyses or whatever it is they're doing, and really help us understand, these new deposits as they're found.
Well, thank you, Simon. I think that's been really insightful, definitely for me, and I hope everybody else out there has enjoyed this episode of Geochemistry. And we will see you all in a few weeks.
Yeah, thanks, Sam.